Hi everybody. Welcome to Universe View Odyssey channel. In 1935, 3 years after settling in the United States, Einstein along with his research colleagues Boris Podolsky and Nathan Rosen, completed the EPR argument that quantum mechanics is not perfect, based on the entangled state of the two systems. This is the famous paper titled Open corner bracket, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? Close corner bracket, published in the magazine Physical Review, number 47. The EPR argument presupposes the principle of locality, which states that an objectively possessed element of physical reality is not immediately affected by a distance. Bohr published a rebuttal with the same title in the 48th issue of Physical Review that year. Since then, Einstein's party and advocates of quantum mechanics, including Bohr, have been debating the century for 50 years over whether quantum mechanics is complete. It will not be easy for the public to grasp the content and meaning of the debate between Einstein and Bohr, in which physics geniuses argue over the validity of advanced theories, especially philosophical theories. In particular, the EPR argument that Einstein put forward after losing 2 debates is so sophisticated that it is not easy to understand the core. Let's take a quick look at the background knowledge to properly appreciate the exciting debate of the century. Spin conservation thought experiment, non-locality. A bronze plaque commemorating the Stern-Gerlach experiment at the Institute for Advanced Study in Frankfurt, Germany. This experiment confirmed that the magnetic moment and spin are quantized and that the act of observing changes the identity of the spin component. Spin implies a strange world of quantum theory. There is a famous physics experiment that helps us figure out the nature of these spins. The Stern-Gerlach experiment proved that the magnetic moment and spin of an atom are quantized, and that measuring the spin of a certain rotational axis destroys the spin information of another rotational axis. It was performed by German physicists Otto Stern and Walter Gerlach and is considered one of the most fundamental experiments in quantum mechanics. By applying a magnetic field to silver atoms with different spins can be sorted out. Now, using these devices, up-spin silver atoms and down-spin silver atoms are sorted. If we collect up-spin silver atoms and put them in an up-down spin sorter, they all come out in the up direction. Now let these up-spin atoms pass through a right-left spin sorter. Then some of these will come out in the right direction and some in the left direction. What would happen if we let the right-spin silver atoms pass through the up-down spin sorter again? Since we've already picked the up-spin atoms, we would expect it to come out in the up direction. But surprisingly, the silver atoms are split exactly in half in the up and down directions. If we put the right-spin silver atoms that came out of the up direction into the right-left spin sorter again, they forget their identity, right spin, in the past and split exactly in half in the right and left directions as the first time. The above experiment is clearly different from the properties of the macroscopic world that we know from common sense. Consider sifting pebbles of different sizes through a sieve with a mesh of a certain size. Assume that 20 pebbles of various sizes are sieved and 10 remain and 10 pass through. As long as the mesh is intact, it is common sense to expect that repeating this operation will yield the same results as the first time. Now, take the 10 pebbles that have passed through the sieve, weigh each one, and divide it into 2 groups, those that are heavier than average and those that are below average. Now, the heavier than average pebble is again sieved through a sieve with the same size mesh as before. All of these were pebbles smaller than a mesh, so of course they will all pass through a sieve this time too. The size of a pebble does not change after being weighed. Conversely, the mass of a pebble remains the same after being measured. This is because each pebble has a unique physical property called size and mass. However, through the above Stern-Gerlach experiment, we learned that spin, a representative physical quantity dealt with in quantum mechanics, does not have such a unique property. Why does the spin of the silver atom change from time to time instead of being consistent like a classical mechanical property? The reason for this is that when the up-down spin of a silver atom is measured and then the right-left spin is measured again, the former spin properties change due to the measurement effect. A pebble is a different situation from the macroscopic world, where the size does not change even if the size is measured and then the mass is measured. This is the canonical interpretation of quantum mechanical phenomena. According to quantum mechanics, the silver atom's up-down spin and right-left spin are related in a mathematical way. A measurement of one property affects the probability of having another property. But about the physical mechanism of the effect, quantum mechanics is still silent. Now let's look at a spin conservation thought experiment. Consider a pair of particles where the sum of the two spin amounts, say O, is conserved. Now, bring these two particles, one on Earth and the other in the Andromeda Galaxy, and check the spin state of the particle over there by looking at the spin state of the particle on Earth. Before analyzing this thought experiment, let's take a quick look at spin. Spin is one of the physical quantities such as energy and momentum possessed by microscopic particles such as electrons. Spin refers to rotation in a clockwise or counterclockwise direction about an arbitrary axis of rotation, and it has a unique property that is different from the rotation of the macroscopic world. In other words, the rotational speed does not change, but the direction of the rotational axis can change from time to time depending on external influences. If the spin of a particle on Earth is plus 1/2, what is the spin of a particle in the Andromeda Galaxy? This is an easy problem. Since the sum of the spins is conserved as 0, the spin of the Andromeda Galaxy particle is minus 1/2. How could the act of determining the spin of a particle on Earth affect a particle 2.5 million light-years away? We can refute the interpretation of quantum theory for this situation as follows. The fact that the spin of the particle in the Andromeda Galaxy is minus 1/2 is not influenced by the observation of the particle on Earth, but it originally had that spin value. It's just that when we took the particle to the Andromeda Galaxy, we didn't know that the spin was minus 1/2. In a word, it is an argument that the strangeness of quantum mechanical phenomena is only due to our ignorance. However, this is a very naive counterargument, because there is a lot of experimental evidence to put this objection to rest. First of all, let's apply the spin sorting experiment of the silver atom described above to the spin conservation thought experiment. A pair of particles, one on Earth and the other in the Andromeda Galaxy, are placed so that the spin sums to 0. When we measured the up-down spin component of particles on Earth, it was up spin. Therefore, the spin of the Andromeda Galaxy particle must be down spin. Then we measured the right-left spin of a particle on Earth and it came out with a left spin. Then the particles in the Andromeda Galaxy would be right spin. Therefore, it can be assumed that the up-down spin component of the Andromeda Galaxy's particles is down spin, and the right-left spin component is right spin. In fact, if you check the particles of the Andromeda Galaxy, you can confirm that it is as you guessed. Now take the Andromeda particle and repeat the spin measurement as before. According to the logic of original spin, particles from the Andromeda Galaxy should have down spin and right spin. But, after measuring the up-down spin component, the up spin and down spin values come out with exactly half and half probability. Of course, even if you measure the right-left spin component, right and left spins appear with half and half probability. Why does this result? This is because, as the Stern-Gerlach experiment already says, the second measurement act completely erased the first measurement result. This is interpreted as a result of the uncertainty principle, which states that not only particles do not have inherent spin properties, but also that the act of measurement affects the physical properties of the observed object. Let's go back to the spin conservation thought experiment from earlier. Opponents of quantum mechanics, such as Einstein, questioned the interpretation of quantum theory, saying, how can particles in the Andromeda Galaxy, 2.5 million light-years away, be momentarily affected by observations of Earth particles? And their interpretation of this situation is as follows. Originally the spin of the particle brought to the Andromeda Galaxy was minus 1/2, but we just didn't know. However, this is not the right interpretation in the example above. The act of measuring the spin of a particle on Earth momentarily affects a particle in the distant Andromeda Galaxy. Readers simply do not realize the seriousness of the situation if they simply regard it as a hypothesis. This is actually a fact confirmed through experiments. This is what is actually happening in our universe. Now let's go back to Einstein's ambitious EPR argument designed to attack quantum mechanics. This caused a tremendous repercussion in the physics world at the time, and 20,000 papers were poured out over 50 years related to this debate. It was truly the debate of the century. This debate ignited in 1935 and turned into a philosophical debate, but in 1960, John Bell devised Bell's inequality, which could be confirmed experimentally, and turned into a physical argument. What Einstein argued in his argument was that nature has definite properties, but quantum mechanics is incomplete and therefore fails to describe them properly. However, in 1982, the argument was experimentally confirmed by French experimental physicist Alain Aspect, shocking the world physics community. Einstein was defeated, and it was confirmed that this universe, contrary to the beliefs of Newton and Einstein, had an uncertain and strange appearance with no definite properties. Thanks for watching. You can read this story in Injury Time, injurytime.kr.